So here you have to prove that if n is strictly greater than 1, these n power 4 plus 4, this is composite.
Composite, that mean two.
Not prime. You have to give a factorization.
Mm,
Yes.
mm. Oh, log equal to 1.
So the thing is, we will try to factorize it. So we'll add and subtract some quantity so that I get some factorization, right? So this n power 4 plus 4, this I can write it as n square whole square plus 2 square, right?
Mm. Yeah.
So if I want to make it a whole square, I need one more term, right? It's the 2ab term I need. So 2 times n square times 2. This term I need, right?
Mm.
And if since I have added that, I have to subtract that to adjust it. So it's 4n square,
Mm.
right?
Yeah, yeah.
So the first three terms, so that will give me the whole square, right? So n square plus 2 whole square minus 4n square I can write 2n square whole square, right?
Mm.
So now I can use that a square minus b square formula.
Yeah, yeah, yeah.
So 2 plus 2n
Mm.
and n square minus 2n plus 2, right?
Mm. Mm. Yeah, yeah.
Now this is a factorization, but I have to show that each of the term is strictly greater than 1, right? Otherwise it can happen that one of the term becomes 1. So how to show that? Then only I can say it is composite, right?
Wait, this is factorization.
Right,
So if greater than one,
right,
we just prove that the term is each term is greater than one.
right. That you have to show. Each term is greater than 1.
Oh, yeah, 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 yeah. So we use the way to the second polynomial
Yes, yes.
is right.
The yes, that you have to think, because this condition you have to use now, that n is strictly greater than 1.
Mm.
Because if you check that if I put n equals to 1, then this term is actually 1, right?
Mm.
So that will not work. That's why they have given the condition n is strictly greater than 1. So if n is strictly greater than 1, then this part is always greater than 1, because everything is addition, right? So I have 2 here. But how to tell about this one?
Mm. Swear. Greater than this. So we have n square that's a n plus one, n minus one square plus one.
Okay. Yes, so what I can do is, so we can do separately. So n square minus 2n plus 2, right?
Yeah, plus
So
one minus one. Yeah.
yes, yes. So the thing is n minus 1 whole square plus 1, right?
Mm.
So this is greater than 1, because n
Mm.
is greater than 1,
Mm.
right? So hence this part is n power 4 plus 4 is a composite, right? The next one is, so prove that every n that is greater than 12 is sum of two composite numbers. So I can always write number greater than 12 as sum of two composite numbers.
Mm. Greater than tail. Hmm.
Yes, greater than 12.
Sum up two composite number. Hmm. Hmm. We have this. Hmm. Tail. Tail is 6 plus 6.
Yes, yes, 12 is 6 plus 6, that is thing. But yes,
6 plus
any number you have to write. So what you can do is,
11. 13. 13 is 6 plus 7, not
no,
7.
no, that is not possible. Any other expression you have to think.
4. 4 plus
9.
9. Uh,
Yes. So that we can write. Yes. So you have to, here you have to break into two cases. So one for n is even and one n is odd.
mm,
So let us. So what you observe that we can do.
mm,
Yes. Tell me how to do. So suppose n is even.
wait. Evan. Evan. Evan is 2, is right? 2, 4. Yeah.
Yes. Yes. But you have to write it as a
Yeah.
sum of composite number. Yes.
Mm. Evan greater than
12.
12. So we just 6 uh, plus 6 plus n 2.
Yes. Yes. That you can do.
That's uh,
So 6 plus n minus 6, right?
yeah, yeah. 6 plus 6 plus 2 2 something. Yeah. That's
Yes, yes. So the thing is 6 plus n minus 6. So this part is always even, right?
mm,
Because n is even. And it is also greater than,
this 2 2k. Yeah.
right? Okay. So this is fine.
Mm,
What about odd?
mm,
If n is odd, then you have to,
odd.
right? So if n is odd, then we have to do something. Same idea. You have to find a number. So
Mm,
since it is greater than 12, we have to find composite
mm,
sum of two composite numbers.
mm, mm, mm. Oh, we have 4 is right. 4.
Okay, but the thing is, if you take 4, 4 is an odd number, right? Sorry, 4 is an even number. So, and n is odd. So, it plus the other thing is odd. So, you cannot always make sure that whether it will be
Yeah.
either a prime number or composite number, right? So, you have to take something odd out first.
So we have 13, 15, uh, 15.
So, you can take out an odd number such that the remaining part is even and that you can make sure that it is always composite.
Uh,
So,
So,
for example, I can take 5 out, right?
mm,
5 I can take out, right? Always, since it is greater than, so I can write as 5 plus n minus 5, right?
but 5 is not composite.
Yes, so that is the thing. So what, which odd number we should take?
Yeah, yeah, yeah.
7 will also not work, but 9 can work, right?
9, 4. So 4.
Right. 9 can work. So 9 plus n minus 9, right? So since n is greater than 12, So n minus 9. So this is also greater than 2, right? And is even always. So this part is always even, right? So it is a sum of two composite numbers, right?
Even, even. Yeah, 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 yeah. Mm,
Okay.
mm, yeah.
So this is fine, right?
Mm.
Okay. So next one is prove that if 2 power n minus 1 is prime, then n is prime. So you have to show that if 2 power n minus 1 is prime, then n is prime.
Uh, 2 power n minus 3 a prime.
Yes.
Mm, mm, 2 power n. Mm. So we should use induction, is right?
No, induction it will not work, right? Because you have to show that n is prime. Because
Mm,
if you are given some condition amount n and you have to show 2 power n minus 1 is a prime, then maybe induction will work. But here it is the opposite thing, right?
mm,
Because induction will not work, I think. Here. So I think you can use uh, the contrapositive thing. So contrapositive, you know, right?
mm,
So this is suppose this statement is P and this statement is Q, right? So here I have to show P implies Q, right? So the contrapositive is not Q implies not P, right?
mm,
So if I assume that n is composite, then I have to show that 2 power n minus 1 is composite.
mm, mm, mm.
If is n is composite, then 2 power of n minus 1 is composite. So now I think it is easier to check. Yes, now how to do?
Composites. So that's the AP.
Right.
Oh,
So since n is composite, I can write it as product of two things where both a and b are strictly greater than 1.
mm.
Yes. Then what happens to 2 power n minus 1?
2 for AP.
Right. So here we have a factorization, right? So it is 2 power a whole power b, right?
Mm,
Minus 1. So this I can write it as 2 power of a minus 1 times 2 power of a b minus 1 plus b minus 2 and so on up to 2 power of a plus 1 like this, right? This is the factorization.
oh, I don't know it.
Oh, this one you okay. So this one I think this you can check easily. So the thing is, you know the factorization of 2 cube minus 1 like this, right?
Mm,
So here is just we are using uh, the thing is here this quantity you can just take as a variable. So for example, x minus 1, right?
mm,
X minus 1, this is the factorization is x minus 1 times x power of n minus 1 plus x power of n minus 2 like this, right? This factorization you know, right?
yeah, yeah.
So now here just you substitute x equals to 2 power n. Then you can and n equals to b. Then you can see that it is same.
Mm, yeah, yeah, yeah. It's minus 1. Maybe 2. Yeah,
Okay,
yeah, yeah. Okay.
right. So this thing is so here you can check that this part is also strictly greater than 1 and this part is also strictly greater than 1. right? Since a and b are strictly greater than 1,
Mm.
so all of them are strictly greater than 1, so this is composite, right?
Mm.
So from this, so this implies 2 power of n minus 1 is composite,
Mm.
right? So this is what we wanted to show, right?
Yeah, yeah, yeah. Mm.
Okay. Okay, let us see an application of the Euclidean algorithm. So suppose we have two 826 and 1980. So we have to find the GCD. So how to use the Euclidean algorithm? Tell me.
Mm. So we minus this. Yeah, that's the one is 90 minus two.
Yes, 1890 we first express, we
E-
divide by 826 and find the quotient and the remainder, right?
yeah, yeah. Equal to a 26 plus something. Yeah.
You know how many times it will go? You have to find the quotient.
Uh, two, two. Yeah, I think
Yes, two times.
two seven.
So 2 times 826 plus,
Mm. Plus how much? One a
what is the remainder?
one a 50, two a two a two six, two three a.
Yes, 238. So the next step is 826, we have to divide by 238, right? So how many times 238? Oh, this will go here and this will go here.
Mm, two, three, 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 and one, one, two.
Right. So it is 3 times and 112. So next
Mm,
step is 238 equals to,
2,
right, 2 times 112 times plus
14.
14.
A, zero.
Yes, 8 times. Zero. So the yes, so the GCD will be this one, right?
Mm,
So this is the GCD. So now, suppose so you want to find the linear combination. So use the Euclidean algorithm to express GCD as a linear combination
mm,
of the two numbers 826 and 1890. So I want to find 14 equals to 826x plus this type of expression I want to find. So what will be x and y?
Mm.
Right. So we can use the Euclidean algorithm, right? So let me show you. So 14 I can express as from the Euclidean algorithm.
Mm.
So it is 238 minus 2 times 112, right?
Mm.
So the next step is I will replace this 112 from the previous line, right?
Mm.
So this is 238 minus 2 times 112 will be 826 minus 3 times of 238, right?
Mm.
This is what I get from the previous line, right?
Mm.
So now if I simplify 7 times 238 minus 2 times 826. Clear up to this one?
Mm.
2 and 3, 6, right?
Ah, yeah,
6
okay,
plus.
okay, okay. Mm.
Right. So next step will replace 238. So the 238 I will get from the previous line. So 1890 minus 2 times of 826.
Mm.
Right. 7 times 1890 minus 16 times 826, right?
Mm.
So this is my linear combination, right? So what I get here is, so x equals to minus 16 and y equals to 7.
Yeah, yeah. Mm.
So this is clear, right?
Yeah, yeah. It's okay. Mm.
Right. So next we define what is the LCM of two numbers. So we saw the greatest common divisor, right? So the next is the least common multiple.
Mm.
The least common multiple denoted by LCM of two integers a and b is denoted by this box a comma b. Okay,
Mm.
and it is defined by, so this will be ab divided by the GCD of a comma b. If a not equals to 0 and b not equals to 0, and it is 0 if either of them is 0. Okay,
Mm.
so the definition is fine, right?
Mm. Let's. Mm. Mm. Please come on. Please,
Least common multiple.
please come on with the why. I think I know it was yeah, a little bit confused about English. Maybe.
Yes, so least what.
You give an example? Maybe
Yes, yes, example
remind me.
we'll see.
Yeah, remind me. What's it?
So yes, so why it is called the least common multiple is, so greatest common divisor, it was, why was the name greatest common divisor? Because that number was the greatest number that can commonly divide both of the numbers. That's why it is called the greatest common divisor, right?
Mm.
And this one is called the least common multiple because it is the least number that
Mm.
is a common multiple of both of them. Common multiple means it can be divisible by both
Ah,
of these, right?
we mean
That's why it is called the least common multiple.
we mean multiply them and divide by GCD.
Right. The example we'll see. Example is, suppose a is 3 square times 5, and suppose b is 2 square times 3 plus 7, right? Then what is the least common multiple? So the LCM will be. So what is the GCD? Tell me first.
GCD is 3.
3, right?
Yeah, 3 only.
Because 5 and 7, 2 are not common in each of them, right?
Mm.
So it will be 2 square times
Mm.
3 cube times 5 times 7 divided by 3, right?
Mm.
Right.
Mm.
Fine.
Yeah, it's okay. Mm.
Right. So this is the example. So the following property what you have is, so if you remember, in case of GCD, 1 minute. Yes. So GCD, if you remember, we defined it's the minimum of the exponent, right? Yeah, I'm not yes, this one.
Mm.
So if this is one prime factorization of A and this is the prime factorization of B, then the GCD is the minimum of AI and BI, right? This is how, right?
Mm. Mm.
So similarly, we have an expression for LCM. So right. So the first property is, so if A equals to I equals to 1 to infinity, pi to the power ai, and B I equals to 1 to infinity, pi to the power bi is the prime factorization, then the LCM is nothing but I equals to 1 to infinity, pi to the power ci, where ci is the maximum of A and
Mm.
B, ai and B. Okay,
Mm. Yeah, yeah. Mm.
right?
Mm. Yeah.
Okay.
Mm. It's okay.
So yes, a few more properties what you have is, so the thing is, so suppose you take the GCD of AB and take C and find the LCM, right? So this will be same as
Mm.
finding the GCD of LCM of A and C and LCM of B and C. So this is how it works.
Oh. Mm.
Okay. So this,
Mm. Makes sense. Yeah, I think so.
right?
Yeah.
And the third property is, so if you take the LCM of A and B and C and find the GCD, so that will be, the GCD will be outside now. The LCM of A and C, LCM of B and C, and then find the GCD.
Oh. Oh. I see. Uh,
So actually, this part is easy. Actually, you can use this prime factorization technique,
mm.
and the GCD is the minimum and the LCM is the maximum. So just you have to play with the exponents,
Mm.
and you can check that these two properties holds.
Yeah. Yeah.
So these are the more or less the property of LCM. So maybe you can see one application. So prove that the GCD of A and B is same as GCD of A plus B along with the LCM of A plus B. Yes, try to prove it.
IP. A plus B.
Right.
So we New the factorization drum for the right hand side is right.
Okay.
A equal to B y A B and here A plus B A plus B so we can take the minimum outside.
Hmm. Yes, yes, yes. So we can use the factorization, but that will be complicated here. So we
Come on.
can use. Okay, so we'll try to do case by case.
Yeah.
So the first what we will do is, so suppose in case of A and B, we assume that let the GCD of A and B. So this is one. We'll assume first this case, right? So then we'll show that the GCD of
Mm.
A plus B and LCM of A plus B. So this is also one. We'll show this one, right? Now since the GCD is one, I know the LCM by the definition of LCM. It is AB divided by uh, the GCD of AB, right?
Mm.
But since it is one, it is nothing but AB, right?
Mm.
So this now change to your A plus B comma AB, right?
Mm.
So this I have to show it is one, right?
Mm.
Okay. So we'll go by contradiction. That suppose P divides the GCD.
A, B, and A multiplied B is equal to 1.
Yes, tell.
Just A plus B and AB is equal to 1.
Yes, yes. So we have to prove this one that the
Yeah,
GCD of these two things.
that's same maxim, but we need to prove it, right? Yeah.
Yes, yes. This we need to prove.
Okay, okay. Yeah.
Right. So that's why you're assuming contradiction. Suppose some prime divides this one, right? We have to show that it has to be one. So that is a contradiction.
Uh,
So P divides this one. So this implies P divides A plus B and P divides AB, right?
uh,
Right. So now since P divides AB, I know by a property that this implies that P divides A or P divides B, right?
uh,
So without loss of generality, we'll take that suppose P divides A. Then P divides A plus B minus A, right? Because P divides individually A plus B and A, right?
wait, B divided to A, then
Right,
AB minus A.
right.
Oh, 1. AB minus
No, no, I'm saying that so P divides this quantity, right?
A.
And P divides A also. So their difference also they will P will divide, right?
Hmm.
Okay.
Plus or minus is the same, is right?
Yes, yes. Anything. Their addition, subtraction, everything will P divide, right? Because P divides individually those quantities.
Okay, okay. We have common term between.
Right.
Yeah, yeah.
So this will imply that P divides B, right? Because A plus B minus A is B.
Mm.
So P divides A and P divides B. So this will imply that P divides their GCD also, right? That is P is a common factor. But that is not possible because we have started with that they does not have any common divisor. GCD of AB is 1. So this is a contradiction, right? So this implies that the GCD of A plus B and AB has to be 1.
Mm.
Okay.
Yeah, yeah.
Right. So same idea. So now suppose the GCD is not 1, then what will happen? So suppose the GCD is some G, right?
Mm.
So if the GCD is G, AB is G, then I can write A as some GM and B as some GN, where GCD of M and N is 1, right?
Mm.
So I can actually take out everything. So this term A plus B comma AB, not AB. So this is now the LCM of AB. So this is now G times of M plus N, and AB is GMN, right? So I can take out G because it is common in both of the terms, right?
Mm. Yeah, yeah, yeah. Mm.
Right. And on the other side, what I have? Other side I have AB. So AB is nothing but G, that is the GCD, right?
Mm.
And I know that since GCD of Mn is 1, so this part is 1, right?
Mm.
So this is G, and G is nothing but the GCD of AB.
Mm.
Okay.
Yeah, yeah. Mm.
Okay. So today we'll stop here then. Okay.
Yeah, yeah. Mm.